We're attempting to develop forecasts for about 500 million store item combinations every week, stretching out over a 52-week horizon for each week of those 52 weeks. And as you can imagine, that's a really big forecasting problem. But we actually have a fairly tight time window to be able to develop all those forecasts. So on Tuesday, we collect our data. We will go through a long feature engineering process to build out the features that are going to be consumed by our machine learning algorithms. After we've built out the features, we're going to take those features, run them through the machine learning algorithms, and develop model objects. And on Saturday, we have about a 12-hour window to build those features, develop the forecast, and push the forecast to the downstream system. So throughout this entire process, we're extremely constrained on time. And the problem is only going to get bigger as Walmart itself gets bigger and holds more store item combinations. The GPU acceleration we're seeing in the case of random forest and in the case of gradient boosting machines is on the order of 100 to 1. So you can imagine that really enables you to do a lot that you simply would not be able to do otherwise. The superior technology enables us to generate better forecasts. With gradient boosting machines, we can find small-scale effects, such as an extra lift for chayote squash sales in the Louisiana region in Thanksgiving, that you could not do with something as generic and broad-based as a state space model. So you need powerful algorithms that can detect that sort of local anomaly in sales patterns for a very small subset or even only one item out of the 100,000 we sell. There's a great deal of computation required to do that, and GPU technology is what enables us to do those computations. So we've been really excited to work with NVIDIA's Rapids team on directing the development of Rapids and testing it out. And we're looking to move our entire production pipeline into Rapids over the course of the next 6 months.
Hi everyone, this is Nick and I'd like to welcome you to a quick demo on how you can leverage NVIDIA's GPUs within the Cloudera data platform to see massive speed increases in running Spark workloads. Throughout this demo, we're going to be working in CDP Private Cloud, which you can see here gives us access to a wide variety of installed parcels. In our case, we're going to be focused on Spark 3 with Rapids. Going into the details of our cluster, we can see that there are 4 nodes running each with 2 GPUs, giving us a total of 8 NVIDIA GPUs in our current deployment of CDP. To get a good baseline of what a traditional non-GPU Spark job looks like, we're going to remote into one of our nodes where we place a script that executes an example ETL Spark job. Here you can see the input parameters that we're passing this job. And the most important thing to note here is that we've disabled Rapids support so that we can benchmark how long it takes running on CPUs only. This Spark job is calling a Python file named doanalytics.py. We'll be using the exact same Python file throughout the demo for consistency. With the job executing, we're going to go check our resource manager to confirm that it's begun crunching. In the interest of time, we'll go ahead and skip to the results, since most viewers would likely not want to wait the 2 hours and 13 minutes this job took to fully execute. Now, let's go back into that same node and run the same Spark job, only this time, we're going to enable NVIDIA Rapids support. Note that we're running the exact same Python file, only changing an input flag. With the job launched, we're going to go back to our resource manager and take a look at the details of our run. We can see that all the functions being called are prefixed with GPU as we explore the execution plan. We can also check our cluster status and see that all 8 of our GPUs are currently being used. This time, however, we don't have to wait too long to see the fruits of our labor, as the GPU accelerated Spark job only took 3 minutes and 9 seconds. That works out to be a little more than 44 times faster. A game-changing speed increase that opens the door for new opportunities in a landscape where data throughput seems to be increasing exponentially. This is all thanks to the amazing technology of NVIDIA's GPUs and Rapids framework, all running within Cloudera's data platform.
Good morning.
Good morning. Morning, everyone.
Hi, good morning.
Morning, all right. Right, shall we start?
Yes, yes. Go ahead.
Ladies and gentlemen, distinguished guests, good morning and a warm welcome to all of you joining us today. This is my utmost pleasure to serve as your MC for this highly anticipated webinar. My name is O'Neill, and my role as the program coordinator of the Malaysia Project Management Community. I'm honored to be part of this remarkable event. Some of us participated in our previous webinar hosted in March, titled AI for Real-World Applications. Build your own next-gen AI system. It was an eye-opening exploration of the limitless potential of generative AI and its practical application in solving real-world problems. And today, we have the privilege of delving into another captivating subject, modern data science using GPUs. Effortless decision scaling for enterprises. Throughout this webinar, we are fortunate to be guided by the expertise and insight of our esteemed presenter, Dr. Deb Goswami, a big data structure AI technologies from NVIDIA. Dr. Deb, well of knowledge, promises to enrich our understanding of the topic and inspire us to venture into new frontiers of data science. I would like to extend my deepest gratitude to our co-organizers, NVIDIA and Novorient Sdn, for their invaluable support and collaboration in making this event possible once again. It is through such partnership we can foster innovation and drive meaningful progress, benefiting you and me, professionals from various disciplines and industries. I would like to take this opportunity to encourage all of you to actively participate in today's session. Feel free to ask questions, share your thoughts, and engage in insightful discussions. We have a dedicated Q&A session with Mr. Deb's presentation, and you can easily type in your queries or upvote existing questions using the Q&A button in the Zoom. And now, it is my honor to invite Mr. Etiken, the Director and Technologist at NVIDIA Asia Pacific South Region, to deliver a warm welcoming speech. Over to you.
Thank you, the MC, and also to all the audience who are here, eager to learn how data science being transformed by using the general purpose GPUs for data analytics. And next is to Jacob and the team there in Novorient, who has actually organized the session and partnering with us for continuous sharing of this Tech Talk series that we are doing it every 2 months. So thank you for everybody. So what I would like to share with is the journey of analyzing this data has started many years ago. And the three major components of the mantra is basically the algorithm. And the algorithms getting smarter and smarter, and as the ability to understand the data, to analyze the data and bring the intelligence out of the data that is looks at, right? And this evolution has been going on for many years. It's not only in the last couple of years, it's more than 20 years. So for example, GPT is another example of an algorithm. So the evolution of algorithm is a key component. Next is data. I think the big data journey started, I would say easily 20 years ago, or if not the last 10 to 15 years. So we have a mechanism to collect digital native data for last 15 years or 20 years and so. And the third one is evolution of compute capability. Today, 10,000 GPU cars, you can easily get it running on NVIDIA GPUs. But what NVIDIA has done is this 10,000 GPU cores in a single GPU card is not sufficient to keep up with the growth of data, especially digitally, a digital native collected form of data, and also the complex algorithms, which goes into trillions of nodes in terms of neurons in order to do data analytics. So in order to keep up with this, we have scaled not a single GPU, but not only a DGX, which is 8 GPUs in a single system, or HGX in a single system, but we have connected multiple DGXs, which spans into not thousands, but now into tens of thousands of them. So the parallelization, those who are in the parallel world, you know, there is always an Amdahl law, right? So how do you circumvent the Amdahl's law and allow compute across many nodes? That's what NVIDIA has done together with the community, with all our partners. So we have the three good combination. We have very good, complex, smart algorithm. We have huge amount of data. And the next, we have the compute capability to support these analytics. And we brought in as a base platform in order to do general purpose computing. So today you can run Python in a GPU. You can run any AI algorithm without even writing a single CUDA code in a GPU. So the generalization of languages running on top of GPU has become a norm. And one part of vertical that we will be covering today is in terms of data analytics, which goes into many industry vertical. It could be in terms of finance, it could be you know, in telecommunication space and so forth, where you have huge amount of data to be analyzed in a fraction of time, including we call consumer internet space, right? So GPUs are today used in many of these companies, from telco, from banks to consumer internet companies, to understand and analyze the data so that they can make at millisecond timely information extracted for decision making, right? So for example, if you're doing click-through rate analysis, right, they need to look at billions of points, if it is not hundreds of billions of points, to understand what is the best recommendation should be done, right? To go through hundreds of billions of record to see whether there is fraudulent transactions going to happen, so that you can prevent before it happens, and so forth. So that's the power of GPU, together with the full stack solution that NVIDIA provides, that each and every vertical in industries can use it today without touching the CUDA layers or the lower layers of the software frameworks. So I hope today Dr. Dab will, who is part of the team. So we have a group of technologists working with different companies, with the hands-on, with the team there, with the R&D team and development team. He will be able to share our experience in this particular space. And we hope this knowledge will help your journey. If you have an R&D team in your company, feel free to reach out to us or through Jacob. We'll able to look at your projects and how we could assist you. If you have a need, if you want to work with our ecosystem, we have a large enterprise ecosystem partners, SDPs, and so forth, which we can bring them to you so that you could benefit and leverage the whole full stack solution from NVIDIA, enterprise grade solution for your specific need. With that, thank you very much, Jacob, for the work, and also the MPC team who's doing a fantastic job organizing this series of Tech Talk. And I hope it benefits everybody with Dab's presentation after this. Thank you once again.
Thank you, Dr. Atikan, for gracing us with your presence and your sharing. Without further ado, let us embark on this enlightening journey as I invite Mr. Dab to share his expertise and shed light on the fascinating world of modern data science using GPUs. Mr. Dab, the virtual floor is yours.
Thank you very much, O'Neill. I'm going to start sharing my screen, so let me know once it's up and running. And you should be seeing my slides now.
Yes.
Okay, fantastic. Thanks, O'Neill. Before we begin, it's always good to get a feel for how familiar you may be with the power of GPUs. So we've got a poll that we are just about to launch. If you could take a couple of minutes to answer the question whether you're actually using GPUs for your AI and data science development work today. All right, so take a couple of seconds as you think about it, and just very simple choice, yes, no, I'm not sure, and give that a whirl, okay? In the meantime, what I'll do is I will provide a bit of context about NVIDIA's journey as an AI company, our identity, who we are, and how you should think about NVIDIA today, right? Okay. So the results are coming in. But in the meantime, one of the very interesting things about NVIDIA is that our journey as an accelerated computation platform began 30 years ago now. In fact, we're exactly 30 years old today. And Jensen, our co-founder, one of the 3 co-founders and CEO, is one of the longest serving CEOs out there today. And our philosophy is very simple. We want to make the tools and the platforms that allow the smartest, most capable, most innovative people on the face of this earth to do their best work. Yeah, very simply put, that's our mission for the organization. And how we do it is across a variety of sectors, right? The results are in, and I think it's a pretty even split. So I think 24% if you do use it, so that's fantastic. Some of you don't, and some of you aren't sure. So for the not sure and knows, let me try and provide a bit of clarity. What you're seeing on the screen for you right now is a slide of how to think about NVIDIA today, right? Right at the bottom is our hardware stack, right? The chips that we make. And we make GPUs. We also make CPUs and data processing units. And this takes people a little bit aback. They're not as aware of these offerings. So for those of you, any gamers in our audience today, you may have known of us as a GPU gaming company, and we are certainly gamers at heart, but we haven't been just a gaming company for nearly 2 decades now, right? And the journey began in the early 2000s when people started using our GPUs for new and interesting things. If you had visited or viewed our keynote in the GTC this spring, you may have heard from Jensen. And his philosophy was, we started out as an accelerated compute company, and computer graphics was the most mature workload at that time, 30 years ago, right? That's certainly changed a lot with the advent of AI and big data and analytics. And our presence in media and rendering is very well known. What I'm about to share with you today, and I'm super excited to do that, is our journey as it pertains to machine learning, data processing, inferencing at scale, and powering some of the largest AI workloads on the planet today. Right? Sitting on top of our hardware is a slew of acceleration libraries. We have over 150 SDKs out there today. And they're not new, right? Some of these are mature, some of these are very industry standard. Some of these power your favorite tools. Some of these power your favorite companies. And they do this across a variety of verticals. Today, we'll take a deep dive into something called Rapids, which is a collection of libraries and frameworks that allow you to accelerate your data, your big data and analytics workflows, your traditional machine learning. So that journey is something that we have been cultivating for a while, and I hope to share more. Okay, so let's take a brief pause and delve into a theme that Etiken alluded to, Dr. Etiken alluded to in his intro speech, where he spoke about the 3 axes of accelerated, of huge amounts of data, more sophistication on the algorithmic side of things, and the availability of computational power to make these data and algorithmic combinations a reality. So today in the modern internet-centric, e-commerce-centric ecosystem, we have nearly every facet of decision-making that participates or has a stake in AI for decision-making. And that's what fundamentally analytics is, right? Data analytics pertains to this particular philosophy where you're saying, I wish to make a decision, I wish to make an informed decision, and I'd like to make it at scale. As human beings, when we had one-to-one interactions with audiences, or even our one-to-many interactions with audiences before the internet era, it used to be a local cohort. So if you're going to your shopping mall, you might see the salesperson or the strategic store coordinators who have an insight into how people behave. When you start taking that kind of behavior online, suddenly you lose out on certain parts of the data. So think about it. For a sales journey, you'd like to fulfill your targets. You'd like to sell the best product. You'd like to be customer-centric for your customers. You do it with a human being. You pick up non-verbal cues. You pick up expressions. You pick up on what they're saying. You pick up on a lot of hidden signals. When you have that kind of interaction taken to an online space, to an e-commerce space, you're looking at a purely digital set of signals. How long did they hover over this product? What was their search query? If it's a more free text platform, were they searching for things to do, things to sell, things to buy, or things to just know about? So the variety of use cases that people use the same platform for, combined with the amount of data you're collecting around these interactions, has led to this explosion. So today we see retail organizations look at automating and forecasting their supply chains. So as part of the introduction loop, you would have seen a couple of videos. One of them alluded to Walmart. And they're a massive organization with over 15,000 stores across the length and breadth of the United States. And a simple thing like perishables. How do you ensure that customers, for example, they may have a specific holiday, they may have a specific seasonal holiday, which requires a very specific kind of perishable. Those are the easy decisions. But what about weather? When does a barbecue spike happen? When the weather is exceptionally warm in traditionally cold regions? And how do you ensure that the supply chain of materials, the perishable goods, is optimized for that? Right? So you have a lot more complexity in terms of what you're trying to achieve. You're saying that I need to make sure that the produce is sent in time to the store and the right amount of produce so that it doesn't go stale, it doesn't expire, because that's just wastage. Right? So that's just retail. With financial services, and it's easy with the click of a button to buy items that are worth hundreds, if not thousands of dollars. And that also means there's lots at stake. How do you identify fraud? How do you identify fraud in real time? American Express, for example, globally, their entire real-time fraud detection runs on NVIDIA software and hardware. With telecommunication organizations, they have huge needs. When you talk about hundreds of millions of people hitting the network at the same time, somebody just won the World Cup. I want to send a text message. How do you forecast network performance? A spike like that with a known event is very well known. But if you've got an earthquake or a disaster scenario, which is suddenly sprung up, you have very little lead time. How do you predict the kind of usage patterns that are going to propagate from that? Is there a radius from the incident? And how do you optimize for that, right? With consumer internet, you've all seen ads. One time you just search on your favorite search engine for a specific keyword, and you see ads for that. Of course, the intent is to show you content and material that you are more interested in. Same thing applies for healthcare. How do you speed up drug discovery, which is a very expensive life cycle, very high capex life cycle. For the energy manufacturing segments, you have a variety of data analytics and machine learning use cases that you need to enable in. I'm delighted to tell you that NVIDIA participates in this across the spectrum. We work with some of the world's largest organizations. We work with over 15,000 startups just in our network globally. And what we've found out is that there are three big things when it comes to working with enterprise-grade machine learning. It's time-consuming, it's costly, and it's frustrating. Why? The time-consuming part actually comes to the iterative nature of data science and analytics. Several years ago, I was heading up an AI unit for a regional e-commerce unicorn. And one of the things that we wanted to do was provide better recommendation systems to our customers. What we found out is that in an enterprise environment, when you look at building your features that go into your machine learning model, having that available at inference time, at real time when the customer's hitting your mobile app is a non-trivial task. It requires data engineers to have those features out in production environments. It requires a specific cost-benefit analysis to ensure whether that particular feature is economically feasible to have in real time or not, right? So it's a lot more complex than having a beautiful model in your local notebook versus enterprise grade. And that's very time consuming. The second kind of use case, when it comes to the cost as well, yes, we spoke about one aspect of the time consuming. Naturally, the more time you're spending doing something, the costlier it's going to get. But there are also other dimensions. I think Genkin alluded to the volumes of data that you tend to see these days, and that has a direct impact. If you are very successful as an e-commerce company and you suddenly see a spike in traffic from, let's say, 10 million visitors a month to maybe 80, an 8x increase, right? And how do you auto scale that? If you're on your cloud platforms and you're doing an auto scale journey, how do you ensure that your machine learning architecture and the design for it doesn't scale linearly or, God forbid, exponentially, right? The final thing is a bit of an intangible, but it's frustrating to work with productionizing machine learning. And this takes multiple forms. A very traditional, a very common machine learning organizational structure we tend to see is you'll have data scientists who are responsible for writing the model, creating the algorithmic implementation of a particular business problem. You have machine learning engineers who are responsible for taking that sort of local code and rewriting or refactoring it into a kind of code base that is capable of sitting in a production environment, right? So things like unit testing, things like rewriting code performance bottlenecks. Then you have data engineers who are often responsible for orchestrating the data that the model needs to make a decision and its availability at the enterprise level. Right? And the processes around these are a little bit difficult to navigate. Some teams have all of these working on one problem at the same time. Some teams have a handoff cycle where you have a sequential nature, where you say the data scientist builds the model, hands it to the ML engineer who rewrites the code for production, who then identifies the feature gaps, asks the data engineering support to enable these until you finally go into DevOps, CI/CD cycle. And I'm not even talking about the InfoSec overhead, where your IT security teams, they wish to have a position on, is having this feature in real time available a security risk for us? Is there a data breach risk, right? So all of these challenges increase cycle time and slow down time to insight, right? I mean, there are certain industries where the regulatory overhead is significant, and it is not uncommon to have a machine learning model built, ready for production, and then wait for 6 months, 12 months, sometimes in 2 years before it is out in production, by which stage the machine learning model is probably far out of date. So all of these challenges, how do GPUs help? What can you do with GPUs? A common misconception that I tend to have to dispel at this stage is that you can only use GPUs for deep learning. Well, the fantastic news is, no, you can do data processing. If any of you are familiar with Spark, if any of you use Pandas, if you use scikit-learn in your data science lifecycle, you can use GPUs for that. And it's significantly faster, sometimes 1000x for some Pandas operations, and it scales very well, right? So let me take a quick second to address that point. NVIDIA's scalability journey actually precedes our AI journey. Okay, in the mid-2000s, a specific vertical that was using huge amounts of GPU compute was the render houses. So in the early 2000s, after movies like Shrek, it caused an explosion in demand for 3D animated movies. Some of your favorite childhood movies or your children's favorite childhood movies came out in that era. So movies like Trolls, Shrek 2, these were rendered on 1,000-node GPU clusters, taking 80 man-days to render end-to-end, right? A feature film at that time. And NVIDIA were a participant in that process. We were designing our software, our render scale workloads to ensure that you can orchestrate these complex workloads. So that's our genesis, that's our pedigree in designing scalable infrastructure. Before we even get to the more traditional things like high performance computing, building the Hadron Collider analytics use cases, right? So scale with NVIDIA, performance with NVIDIA is a given. We've done it for the last 20 years now, okay? The second thing that surprises people is, don't I need to know C++ to work with GPUs? No. All of our software that you see today is Pythonic. Yes, under the hood, we've done the hard work of writing the C++ code, the highly performant, optimal C++ code. You can access that using Python, and we'll see later how that works. The third thing is, how do I work with this? Does it only work on specific hardware configurations or no? I mean, our hardware exists everywhere, from the smallest, from under your desk in your local desktop to some of the largest supercomputing clusters, including on cloud, right? So when it comes to the GPU accelerated data science workflow, right, you should think of it using it in three ways. For your data preparation, okay? So whether you're using Pandas, Spark, Dask, or any other data processing tool that is Pythonic in nature, it has a direct replacement for you to use in GPUs. The second thing is machine learning and non-deep learning machine learning as well. So your traditional scikit-learn, the entire corpus of scikit-learn algorithms is available for you to use with the exact same syntax on GPUs. This is probably a good time to introduce the three design principles that we tend to adopt when writing software as NVIDIA. The first one is performance. Okay. When it comes to performance, if you're working with NVIDIA software, it is usually the fastest implementation out there. The second design principle is scale. Whether you're writing code for a single node or 1,000 nodes, as a developer, as a data scientist, you shouldn't need to modify your code much. Okay? The third design principle is familiarity, right? If something exists, if it's best in class, do not replace it. So XGBoost, which is one of the most popular structured AI and most scalable structured AI algorithms for regression and classification out there today, a lot of that was actually written, or the commits came from NVIDIA. Okay, so when possible, we directly improve that. Apache Spark, for example, we directly work with the Spark team. Wherever it is not an ideal fit, scikit-learn, for example, we needed to morph some of the fundamental data structures, so we just wrote a parallel, but we still replicate or create drop-in replacements for developers to use. Okay, so there's no ramp-up time. The third axis when it comes to the structured AI workflows that you should think about is about the visualization and inference. Okay, so whether you are crafting visualizations for hundreds of millions of data points, or you are serving API inference workloads for massive B2C audiences, you should be able to use GPUs for that because they scale very well. I've got a couple of questions flooding in from the chat, and they are more around the themes of, can we have a look at customers that are actually using NVIDIA software today? And we'll go into that. So it's a timely one. So in fact, this is what our landscape looks like. You know, as literally one of the, I think the 6th largest company by market cap today, we have a very scalable approach to things. I mean, we know scale, we do scale, whether it's process or partnership. Right? So there are 3 modes that we undertake when we are scaling our AI ecosystem. Well, the first thing you can see kind of on the left-hand side, 25% of Fortune 100 companies today already use Rapids. And this number is out of date because it's about 2 to 3 months old now, or a bit older. The number is definitely higher. Nonetheless, this is just the Rapids component. When it comes to the AI landscape, so things like conversational AI and Metropolis, it's a lot higher, right? And that's where you will see organizations like Walmart, the BMW Group, Capital One, for example, American Express we spoke about, they use Rapids today easily, and they have been doing for years. And why? We'll get to that, right? The second mode of integration that we do is with existing best-in-class vendors and ISV platforms, right? So whether it's ISVs like H2O.ai, SaaS platforms like them, Informatica, MapR, they have Rapids integrations under the hood. The third mode of integration that we tend to do is working directly with best-in-class SDKs and platform SDKs. Okay? PyTorch, Apache Spark, Splunk, Apache Arrow, CuPy, all of these platforms we work with directly to either integrate Rapids or have the developers know how to integrate Rapids. Okay, so which means that you are probably already using GPUs. So the big takeaway for you as a user of GPUs is to don't think about what can I use GPUs for, or does it work with this library or that library? No, the question you should be asking, and the better way, the more productive way for you to get an answer is, I'm using this, does it run on GPU? I should check that. And more often than not, you'll find the answer is yes, and it has been true for years. Okay. Let's walk through a few examples of people who have more recently, this is an example that encompasses that, right? So we've got Adobe, who's an enterprise client. They're running Databricks, which is an enterprise software suite, and they've got GPUs. And they found that after after transitioning or adding GPUs to the existing Databricks cluster, it resulted in 90% cost savings for them as an organization, along with huge performance gains, right? 7x performance boost. And it wasn't with much code migration at all, right? So this is with almost no code change and a bit of tuning. Walmart, we've already spoken about them. I think they've seen 100x faster feature engineering performance, okay? They've seen 20 times faster model training performance using Rapids, Task, and XGBoost, right? And they've also seen more accurate models. So like I said, because they're able to do faster iterations, they're able to do more development work on the machine learning, they see that eventually they figure out how to eke out more advantages. Because that's the other thing. When it comes to data science and analytics, it is still an empirical, iterative process, okay? Taking a bit of left field for more computational parts of things, so more of our graph analytics piece. AstraZeneca, we kind of worked with them to accelerate some of their drug discovery workloads, right? So it kind of looks at seconds compared to days. That's huge. Right? So imagine the cognitive workflow, right? You're saying, I need to design an experiment. It's going to take me days to run. So you design for that. But now if it takes you a second, you can run so many parallel versions of that and then do compare and contrast. So your entire workflow changes. Your innovation cycle explodes, right? Before I delve into this, I'll ask one of the other, answer one of the other questions that's come up. I can see on the panel, it says, what are the readiness factors for enterprises making decisions using GPU? It's a good question. The answer to that would be, if you are using any modern AI framework, you are already ready. If you have a data science team, you're already ready, right? For example, you don't often think about whether you have a CPU or a GPU in your cluster, right? That's the only thing that changes, whether you're running it on cloud, on-prem, or on your own custom hybrid infrastructure. So the readiness factor was actually bare basics, okay? There's very little barrier to entry. Okay, so we've spoken about NVIDIA, we've spoken about what and how the world uses NVIDIA. What is it? What is Rapids, right? What can you achieve with it? Well, as I said, it's a collection of SDKs and libraries and is across these three axes of data processing, analytics, and visualization. We've also got a few application and domain-specific frameworks. So if you've got signal processing, if you've got image processing or recommendation systems, cybersecurity, spatial analytics, these have, again, specific implementations. And again, we mimic and replicate best-in-class SDKs. Okay, so let's take a closer look at some of these components. Okay, right. So this is a slide that narrates itself, but we'll still go through it step by step. On the left-hand side, what you have is CPU pandas, GPU pandas, and CUDF. And I draw your attention to the syntax. It's identical, right? Some of you do import pandas as PD. If you did import CUDF as PD, you wouldn't even need to change this line. So the syntax of existing pandas is, that's what we mean when we say it's a drop-in replacement. Now, looking at here on the middle or the next 2/3 of the screen, what you're looking at is, by the way, please note that this is a logarithmic scale because we needed to fit in 69 and 1000 on the same slide. Okay, so you can see for various data processing operations, from additions to cumulative sums, all the way to where operations, you see 69 to 1000x increase in performance with the same code. And this is on a 10 million rows data set. Okay, so not insignificant. Okay, a common question I get at this stage is, am I limited by how much data I can fit into a single GPU? Absolutely not. Right? And you can do this multi-node, multi-cluster data orchestration even using pandas by submitting it to a DAS cluster, which has an interface for it. So it's literally however much you can spin up. Okay. Okay, let's have a little look at graph analytics. So cuGraph is a drop-in replacement for Network X. And what this allows you to do is things like page rank and community detection, low vein distance calculations, astronomically faster. It allows you to do iterations faster. It allows you to therefore investigate deeper nodes. So those of you who work in Graph AI will know that the number of jumps, hops, steps that you can use were determine the complexity of the algorithm, right, that you can use. This one here, for example, shows you how you can go from 17 to 4.4 trillion edges, right, and it still scales. And the iteration time in seconds, right? If any of you have worked at this scale, you know that you're talking about days, weeks for some of these larger edge sizes. Okay. Right, now we come to my favorite, QML, structured AI, scikit-learn. The entire scikit-learn, almost the entire scikit-learn portfolio brought into Rapids, right? And you can see the average speed up. So here, what you're seeing over here is a single A100 GPU versus at the bottom side here. You can see the comparison hardware. So a single A100 compared with two Intel processors with 80 logical cores, 40 each. And you're still seeing that outperform by 100x for things like ElasticNet, 1000x for HTTP scan, 18,000 times faster, right, for linear SVC. And you even see benefits when you're doing something like PCA or even random forest, right? And here again, if you look on the left-hand side, from a syntax perspective, very familiar. So if you're using scikit-learn, if you're using pandas already today, literally nothing beyond your import statement changes. Of course, you need to have a GPU in your cluster. And we design with best-in-class frameworks. So if you're orchestrating your nodes using Kubernetes, for example, all of our SDKs just work out of the box with Kubernetes natively as an orchestration platform. And we'll see how that works later. Okay. Another thing that we've just recently added is because we do build our own, we do make our own CPUs, we do make our own supercomputers which have CPUs based on the ARM architecture. We have seamless fallback. So if you have a hybrid cluster, which is what we design a lot of our workloads for, and either your GPU is overused, or you'd like to try this locally before you submit it to your production cluster, you have seamless CPU fallback. It's still a work in progress for all of the libraries, but for cuML, for pandas, for cuDF, you should be able to see that. Okay. Okay, sorry, just a quick question. I think a C1. C1 about how many GPUs were used for the pandas example. Let's go back again. So again, you can see the same thing. So it's a single A100 versus a 48 core processor, right? 1-to-1. cuDF Python versus pandas. Okay, let's talk about accelerated XGBoost. Like I said, whenever possible, we go in directly and improve the libraries directly there. So for XGBoost, your import statement doesn't change. Just make sure that you're using the tree method equals GPU hist. Yeah, and that's it. Now, some of you, I don't know if any of you are on Twitter, but if you are, you should follow Boyan's account. He's fantastic. He's hilarious. He's one of our Kaggle grandmasters and XGBoost ambassador personified. Absolutely fantastic personality and a tremendous amount of expertise. So if you're ever on Kaggle and you need to know how to use XGBoost, look at his notebooks. It's beautiful code. It's super clear, and no one knows how to leverage XGBoost better than him. Okay. It is one of the most explainable algorithms for highly regulated enterprise conditions. A bottleneck with using some of the more complex algorithms often tends to be that you can't explain why a specific decision was arrived at. And this is why for the longest time, linear regression has been a stalwart of enterprise structured AI workloads. It's one of the most commonly used algorithms because it's easy to explain. You can tell an auditory or regulatory body why the model did what it did, right? So with the Shapley support built in, XGBoost has the explainability. The thing with a lot of the regression-based approaches is there's a diminishing plateau effect. The more data you have, the better the model performs is true up to a certain point. Okay, XGBoost is one of the few non-deep learning algorithms that continues to perform as you feed it more and more data. In fact, for structured AI, I always recommend just do not use a deep learning approach until you've tried XGBoost. Okay, of course, deep learning approaches really excel at encoder-decoder type operations or embedding-based approaches, right? If you have enough sample data for your specific use case, structured AI and deep learning is a good fit. Okay. Another area that we have recently decided to make our own internal primitives publicly available is in indexing, right? So for those of you who've had who work in information retrieval use cases or ANN kind of use cases, then you may have known of FICE, which is Facebook's ANN indexing library. It's fantastic. It's one of the best. We're giving that a bit of a performance boost. Okay, so with Raft, we're working with Novus, Redis, and FICE to accelerate their indexing. And of course, this has a direct impact on vector databases. Right? Okay. All right, so now one of the things when it comes with working with distributed data sets and large-scale data processing is Dask. Many organizations use pandas, probably because a lot of these courses that they took online show them pandas. It seems to be easy to use, so let's kind of use it. And they never realized that Dask exists. In the 80s and early 90s, there was this battle between the VHS and the Betamax standard. I don't know if any of you remember. For some of the younger members of the audience, before you had cloud-based streaming on demand, You used to have to go to a physical store, pick up a physical black cassette thing, which had one movie in it, bring it back home, and you could watch that movie, right? VHS and Betamax were competing formats. Betamax supposedly was a better standard, but it lost out to the VHS format, and the rest is history, right? I suspect Dask is one of those. It's better, it's more lightweight, it tends to scale better for a lot of workloads. So if you are looking at scalable pandas kind of workloads, do give Dask a look, and we'll get to that later. Okay, I have a question on my window. It says, how inclusive is Kuriev since it's not a drop-in replacement, and will there be a problem using it with pandas simultaneously? Okay, so the question is wrong. Okay, Kuriev is a drop-in replacement as long as we have a GPU in the cluster somewhere. It is the same syntax, unless you mean you want to run pandas without changing any of your code at all. It's not that, but there are no issues with running it simultaneously with pandas. As long as you're using import Kuriev, in fact, I'll show you in some notebooks later how we have that, there's no issues, right? In fact, it's completely interoperable. What we take care of is using something called the Apache Arrow format. So whoever asked that question has clearly not been listening, but it is a drop-in replacement. So your syntax doesn't change, and it's two different libraries. So feel free to use it as and when you see fit. Okay. What we're seeing in this slide here is how you do get drop-in replacements for a variety of use cases. And what I'm showing you today is a Dask and SQL workflow. And what you're getting to see is 10 to 20x speedups out of the box, right? So now, how does that impact your TCO? How does that impact your infrastructure spend? How does that impact your innovation cycle? These are all questions to think about. And there's a very specific reason why organizations who need a performance boost, who want a cost-saving journey with the infrastructures that scales, they go with NVIDIA, right? The thing is, with a lot of machine learning and AI, it's not a spectator sport, and it's not, and neither is it intuitive. Okay, what do I mean by that? Let me give you an example. 8 years ago now, and I was building a real-time image retrieval product. You have a phone, you're watching MasterChef, you point your phone at the TV show, it detects the scene, it recognizes the episode, and it gives you the recipe of the item that's being cooked. Fantastic. Okay. Thing is, you're kind of looking at retrieving image index vectors at scale. So you have a three-part process that says, I'm going to take my images, I'm going to encode them into an index structure, I'm going to create an index of those features, and once I have an input image, I'm going to do a comparison. Is this image in our database? Which one? Match, return the payload. When you're running it locally, we were getting less than 200 milliseconds end-to-end, right? Fantastic. We loved it. The moment we went to a distributed system, there was a huge amount of overhead. When we started seeing things like, oh, there's 50 requests per second is the workload we're expecting. Suddenly the infrastructure that we had written, the code that we had written didn't work, right? Why? The bottleneck was the network. What we had done is we'd use something called cosine distance, which requires you to download the entire feature set for a specific set of candidates, which is about 500 megabytes per query at that stage. And that's when we found out that it was a bottleneck. Right? So the point I'm telling is, saying is, if you haven't worked at scale, reading Medium blog posts may not help you too much, right? So until you actually do the work, until you've experienced it, some of this will be, okay, I need to work harder to make sense of this, right? But organizations that scale, that know how to do this, that have these conditions, it's a no-brainer. Right? Organizations that have seen this journey where they have spent, even for starting off, the difference between using GPUs in the data analytics stocks versus not. And I'm talking about two-person startups with less than $1 million in funding. They've also seen the benefit, right? So I guess it's important whenever you're encountering things that you haven't heard about before, look at the people who are using it. They tell the story. And with NVIDIA, our journey, I think, is pretty much the journey of the product speaks for itself. Okay. I'm going to skip who's special unless somebody here. So can I have a quick check? So if, just raise your hands. Do you want me to talk about the geospatial parts here, or we can skip through this? Okay, yeah, that's fine. So this is basically for GeoPandas. If you're working with ArcGIS data, then it works with that. Co-signal is another part of Rapids. Over here, what you're seeing is the performance increase for very complex mathematical operations, whether it's fast Fourier transforms, convolutions, resamplings, spectrograms. You kind of seeing huge speedups. And again, our benchmarking suite is the same. We take one A100, compare it against a 40 to 50 core Intel CPU. Okay. Yeah, okay, fantastic. You've got a huge data set, hundreds of millions of edges, trillions of edges. How do I visualize that? Okay, often an issue. Well, if you're using Matplotlib or Datashader, Bokeh, Plotly, all of these integrate natively with Rapids, right? So that's the other thing to bear in mind. If you're using CPU-centric data objects in your development path, and at any stage in your journey, you'll have to transition to a GPU to accelerate parts of that, and that's a common workflow. That's what we've designed this for, right? So, for example, this is what a code migration, quote unquote, code migration journey would look like. Right? If you're using XGBoost, you change it here. If you're using scikit-learn, your input statement changes. If you're using network X, again, your syntax over here, you're just doing a find and replace, right? If you want, you can do import cugraph as NX and do it that way. I highly don't recommend it because it becomes very difficult to debug, right? So just make sure you're explicitly calling it out. That will help you understand which parts you have and haven't fixed. Again, with Spark, we haven't spoken too much about that. We should, we will. Spark natively, we work with the Yarn scheduler to make it resource aware. If you have a GPU in your Spark cluster, the scheduler automatically sends the query components to that Spark cluster, and you get a huge 5 to 10x improvement in performance and an 80% reduction in your TCO with no code change. Right? Don't believe me? Try it out. Okay. So we've spoken a lot about the different journeys. We've spoken about how easy it is to use NVIDIA SDKs. We've spoken about how it scales, how it performs. And you can see all of that here in this one slide, and I'll point you to an additional factor here. Okay. Data load and data prep, data conversion, and the machine learning training. Right? So think across 3 axes. A lot of people are surprised to learn that the single biggest contributor to latency with data processing workloads is not often just the query itself. So just not the computation. It's actually the input-output overhead, right? Serializing and deserializing data objects, compressing and decompressing. So for some of you who work with stream data, like Kafka topics, or you're working with Avro and Parquet file formats, which are compressed, you may not be surprised, but it is a fact that the compression and decompression tends to play an equally significant role in your latency numbers, right? Well, guess what? These things under the hood run 100 times faster. So Snappy and ZSCD, which are the compression decompression libraries, have 100x performance increase on GPU and CPU, right? And that's natively integrated with Rapids. So the purple thing here, so imagine if you used something that was, okay, quote unquote, GPU centric, but just worked on the query optimization part. You would maybe increase this part, but you still have a significant overhead when it comes to data processing and the IO components, right? The data processing itself speaks for itself, right? You're kind of going from 20 CPU nodes to 100. And sure, you see a nice linear increase. 100 CPU nodes is not cheap. Okay, it's not cheap. These days, nothing is. Inflation is a real problem. But the other thing I'd like to draw attention to is the machine learning components. XGBoost stands for extreme. The X, XG stands for extreme gradient boosted trees, right? What does that extreme mean? Well, one of the factors is a huge amount of optimization. So the XGBoost library in and of itself is a tremendously optimized, highly performant library, right? If you look carefully, you can see that as you go from 20 to 100 nodes, it seems like your gains are not really, yeah, I mean, we're not seeing a significant gain, right? So even between 20 to 100 CPU nodes for XGBoost at scale, which is one of the most performant machine learning libraries out there, you are still seeing only a tiny drop. Yeah. Of course, that diminishes completely when you look at GPUs. And we're seeing, okay, this is a 16 GPU 2-node comparison, but if you ran this on a single A100, it would still be faster. So a single GPU competes with 100 CPUs, and that's the way to think about incorporating GPUs. Some people come to me and they ask me, hey, damn, GPUs are expensive. What are you using them for, right? If you're using them once a year and you want to pay full price, sure, they're expensive. But if you're using them to automate about 100 CPUs worth of workload in 50% of the time, not cheap, they're expensive, right? So that's the mindset. And again, it's the same code, right? How does it work? Why does it work? Well, the secret sauce is something called Arrow. We spoke about a lot of the algorithmic computation optimization that we put in place. Of course, everyone knows that GPUs are fantastic at highly parallel tasks. Well, the other thing that we work really hard on is to take care of this I/O overhead, right? So if you look at this left-hand side here, if you've got a pandas object and suddenly you want to use Spark in between, or you've got a Parquet object and that comes into your notebook, you load it into a pandas thing, and then you want to do some scikit-learn, and then you want to send it to some Spark, or you want to visualize it using your Impala backend or something like that. Every time you do that conversion, you're serializing, you're copying, you're converting across its data formats, which it's not an issue when you're working with a 100 megabyte file. But when you're working with a 2 terabyte or 30 terabyte, hundreds of terabytes or gigabytes worth of data, these things add up. Okay, and that's why when we work with the Apache Arrow protocol, which again is open source, along with all of our SDKs, you can get them for free on GitHub, right? We took care of that, so we ring-fenced it. So when you're doing GPU-centric computation, we take care of that optimization. Like I said, we know scale. We've seen this journey many times before. The other thing that's really unique to NVIDIA appliance ecosystems, and this is not something you tend to see. Okay, if some of you recall, we spoke about this use case a few minutes ago about this information retrieval use case and how you were transferring 500 megabytes per query across from the database index to your compute center. That's not uncommon to see, right? And what we do is we've invested heavily in the networking side of things as well. So with Unified Communication X, we essentially bring hardware accelerated computations and communications protocols to that distributed system, right? So even the networking component, if you engage with the NVIDIA appliance stack, tends to see performance uplift. Very easy, brief guide is if you're scaling up and you want to accelerate, just use Rapids, right? If you're scaling out and you want to parallelize, go with Rapids and Task, and you can't go wrong. There are a few other SDKs that I haven't spoken about today in detail. Number, I haven't spoken about QPy exclusively. Number is a just-in-time compiler. So if you've got any SciPy code, you just put in a quick decorator on top of the function you wish to accelerate, and Number, the JIT compiler, compiles that for in real time, in runtime to run on GPU. It tends to work well for local workloads. If you want to do it highly distributed, not really sure it scales very well, which is when something like QPy comes into the picture. So you have SciPy primitives, under the hood, they're all using CUDA to run it in a distributed fashion. Okay. So how do we get started? Very easy. I'll walk you through this. We are good for time, so I'll spend the next 10 minutes, next 5 to 10 minutes, walking you through how you can get started with Rapids. It's as easy as ABC. And again, I believe for the attendees, Those who filled out the survey form, you will get a copy of the slides. So stay tuned for that. It'll come with all of these links. We've got the rapids.ai website. We've also, I would draw your attention to a couple of other areas. One of them is the fact that we have the Rapids GitHub. Go there, look at open issues if you're facing a bug. We've got NVIDIA developer forums. We also have something called the NGC catalog, which has pre-built containers for all of Rapids SDKs and all of NVIDIA's SDKs. Okay. How do you deploy Rapids? Well, we've got a pretty exhaustive deployment documentation, whether you're running on your local machine or your favorite cloud platform or your favorite HPC platform. It's all there. So give it a whirl. It's super simple. It's also available in a lot of these marketplaces. So that's where you can go. Finally, we have our own learning platform. It's called the Deep Learning Institute. It's a bit of a poor moniker. Fundamentally, it's all of NVIDIA's enterprise-grade corporate training material. Some of these are free. Some of these are available for enterprises. In this region, if you're taking the fundamentals of accelerating end-to-end data science workflows, you will have to suffer through me instructing you in this region. But we've got a slew of courses that you can leverage for your teams. Okay, so with that, let's kind of delve into the hands-on demo. I'll show you how easy it is to get started, what you can do, some resources for you to get started, and then we'll make some time for Q&A. Okay. Share my screen again in a second. Okay. One of the things I like about Zoom is you can do this very cool share a part of your screen thing, which comes in handy. All right, so quick check that you can see my screen. It should be a purple, beautiful purple royal velvet color. Fantastic. And you have the rapids.ai website. So if any of you have access to a browser that you can open in parallel, feel free to tag along with me. Okay. Go to rapids.ai and you will be met with this view. It's got a few sample benchmarks that tells you a lot about how and what Rapids does, and you can go to quick start. Now, Rapids, you can install it any which way you want, whether it's Conda, whether it's pip, whether you want to compile from source if you're brave, or whether you want to try out a Docker container. Now, these two are pretty self-explanatory, all right? Those of you who work with condas know exactly what to do. You can basically use these steps. If you want to do it with pip, again, you can. These ones will require you to make sure you have, especially if you're on Linux, if you're on Windows, just make sure you have your latest NVIDIA drivers. It usually takes care of things. I'm going to show you the more complex way so that you kind of know. It's actually my preferred way. I actually prefer working with Docker because it takes care of a lot of the environment issues, right? Which you face even with something like pandas. Okay, so we go to the install selector here. Okay, so look at my screen. You should see this install selector in your screen. It says install with Docker and install selector, and it will take you to this wizard. Now you can use this even for pip and condas. For example, it just gives you the command that you need to put in, right? I'm going to select Docker. I'm going to select x86. I'm running this on my local machine. By the way, I've got a Windows box and I've got Windows subsystem for Linux sitting underneath. So that's how I work. I'm going to go with CUDA 11.8. Do note that everything is backwards compatible. So only with 23.04. So we go with a calendar release. So 23.04 means 2023 April. Okay, so we have a monthly release cycle for Rapids. I'm going to go with stable, and I'm going to go with our NGC Docker container, and it gives me this lovely command. Okay, so I'm going to copy the command, and if you have any installation troubleshooting issues, please have a look through this. It tells us how and what and very common issues that some people face because they haven't really set up the environment properly. Comes up here. Okay. Right, so I'm going to now move to my terminal and I'll show you what I did. Okay, so let's kind of get this out. All right, so what I have here is in this particular window here is where I ran my Docker daemon. So just have it live up and running. Okay, in this part here, let's increase the font size a bit. You see this command here, right? That's what I copied. You look at it, this is what I did. So just copy that in here. Some of you who don't have the Docker permissions, just put a sudo in front of each line. That's the only change you need to do. And for the first time you run this, it's going to download about 10 to 15 gigabytes worth of stuff on your local machine. So two things, don't run this on a mobile hotspot. Don't do this if you're running out of disk space in your local machine or environment, okay? Once you have that out there, you will have a ready container with notebooks ready to go at this address, okay? Which when I click on, let's go back here, it brings you to this kind of view. It's a Jupyter Lab setup. In the background, you have all our notebooks. What you will see on the left-hand side here is all the different components of Rapids that have example notebooks that you can follow. Now, the teams that write our notebooks are either Kaggle grandmasters, they're industry veterans, or they are some of the best data scientists on the planet. So it's a fantastic way to learn how to do machine learning in general and not just the Rapids part, okay? I'll start with cuDF. So you go to cuDF and there's a 10-minute .ipynb, right? What it is a 10-minute introduction to cuDF and Dask cuDF, right? It's modeled after the 10 minutes to Pandas intro, and it shows you how to use cuDF and Dask cuDF, when you should, what you shouldn't do, what you can expect, a few common optimization tools, and it is absolutely fantastic. I'm not going to go through this because it can get a little bit very basic, and honestly, I would encourage all of you to try this out. Some of you would have also noticed that you can try Rapids online over here. So if you have a Google Colab account or a SageMaker account, you can. So give that a whirl. Once you're there, run the 10 minutes to cuDF intro and you'll see how easy it is. What I will show you is what I was doing a bit earlier today. And this is kind of a performance comparison. So we've got a notebook that allows you to do the performance comparison, and we're using a 30 million row data set here. We're just creating it, what you can kind of see, right? And this is running. So just for context, I'm running it on my local desktop, which has a i7 12 core, local 16 core, right? And I've got a 4080 GPU, okay? By the way, you can use our 4080s if you know, for local development if you want. They are not designed, however, to run 24/7. So if you're going to use them for a 24/7 X workload, no guarantees, all right? So this comparison is for a single GPU versus a 16-core state-of-the-art i7 13700, okay? And what you're seeing is cuDF versus Pandas gives you this kind of speed up, 30 times, right? For concatenate, it's about 12 times, 27 times for group by, and 80 for merge, right? When you do it with strings, it's even more significant. For strings, you see at minimum 100x increase in performance, okay? So this is a speed up factor, okay? For UDFs, what you can also see is sort of 140 versus 33. So that's it. That's how easy it is for you to get started with Rapids on your local machine. You can do it today. We have an absolute wealth of notebooks for every single SDK, from cuDF to cuGraph. You've got applications. So for example, if you want to do 550M gens, this gives you sample code with a fantastic boilerplate applications for you to get started with. We've got benchmarks if you need to run. So for example, if you want to run a PageRank benchmark, GPU versus CPU, you can do so. Same thing with all of our other repos, with XGBoost, our demos for XGBoost intro with Rapids, how you can use it, so on and so forth. So get cracking. It's super easy to use. Highly recommend giving it a shot. Any questions, reach out to our forums, or if you have my email, drop me a line. I'll be happy to see how I can help. I think we're just about on time. So I'm going to stop sharing my screen and we can take some questions. Okay. I would like to know use cases for rapids. Well, I mean, so the biggest paradigm shift for you is to stop thinking of rapids as something unique. It's not. It's just data science. What do you use pandas for? You can use rapids for that. What do you use scikit-learn for? You can use rapids for that. What do you use XGBoost for? You can. Right. So any industrial analytics AI use case you can use. Okay. Okay. We've got another interesting question. Could you highlight the potential challenges or limitations that project managers may encounter when implementing tasks in rapids, and how can they mitigate or overcome them effectively? Now, as a project manager, you are going to be managing software engineering teams. So the first thing for you to make sure is that your software engineering teams are trained to use rapids. Now, the syntax is identical, right? But for example, a lot of organizations fail to make the best use of it. So between a technical promise, so we're using 100x increase in performance to, what you see in reality is less, make sure you put in time for your optimization, right? But beyond that, I think it's pretty much a seamless slot-in. A lot of the time, you want to make sure that before you engage in this, your software engineers do take some training on the rapids part. It could be something like this, or just make sure they even go through the tutorials, okay? All right, what are the potential limitations of using rapids compared to traditional CPU-based approaches? Okay. Great question, because we've all been speaking about the good news, right? Well, let's talk about what the limitations are. Well, one of the limitations is for heavily customized, so let's say you're using Apache Spark. Some organizations use Apache Spark too. If you need to use GPUs, that organization needs to have Apache Spark 3 and upwards. Okay? Once you do that, you kind of see a pretty significant improvement in performance. If you're using 2, the architecture for 2 was different to 3, so we worked with the later versions, right? So that's one example. Another thing to bear in mind is when you're using rapids, is that a lot of it is running on GPUs. So if you have workflows where you're shifting in and out of a lot of other libraries that don't use rapids, you probably need to make sure that you're avoiding too much mem copy, because that's when things you're wasting a lot of that overhead. So make sure you're writing your code in a way that leverages even the IO parts of the GPU libraries. Okay, any more questions that I can answer?
Dr. That we have a few more polls. Would you like to launch it?
Yeah, sure. Sounds fantastic. Let's go with the first one.
All right.
To see who's paying attention.
Yeah, we have another second one. I'll launch it here. I just launched it. Can we see?
I can see it. So the question says, types of GPU usage. What can you use GPUs for today? Deep learning, data processing, traditional machine learning, or all of the above? Is this a trick question, I wonder? No, it's not. It's one of the easiest ones.
Okay, we have 45% participants voted. I shall end the poll and share the results.
Very good. 80% of you. Wow, this is a very smart audience. Yes, all of the above. You can use GPUs for deep learning, data processing, and traditional machine learning. So all of these things can be used with GPUs today with the same code you love.
Thank you, Dr. Then we will proceed to the next poll. All right, one moment. The third poll. How to install Rapids?
Oh, this one is a tough one. I wonder what the answer is, right? See, I only give easy questions. This is not an exam, right? So this is just a, how much of the session did I sleep through? Okay.
All of the above is the safest answer.
I think so. I think so. It's okay. It's a Friday. I know some of you are waiting for your early makan break. So yeah, answer the questions and we can kind of go on our merry ways for a wonderful Friday lunch.
All right, we have 58% voted. Let me see the answer. Yeah, the results.
I can't see the results yet, but I'm assuming it's 99% saying all of the above. Yeah.
61%. Let me share the result again.
Okay. Okay. Yeah. See, and this is why. I mean, you can use all of this, right? I always recommend. See, if you're working on vanilla Linux, I prefer to use Conda. Because my virtual environment management, I'm just more accustomed to that workflow. Some people like to use pip, the pip wheels, so it depends on how often you want to orchestrate that. Compile from source is actually for a lot more advanced users. You know, they want to tweak and tune some of these algorithms out of the baseline, or developers, and that's when they do it. The safest is Docker containers, I find, because just Google or search for how to install Docker on your local machine. One of my recommended approaches is Docker, because that tends to get rid of a lot of the headaches around. There's some people, they will install 5 or 6 different driver versions. I don't know why. They will do it, then they will complain and cry and say, oh, this doesn't work, that doesn't work. Or they will install the wrong version. So easy for you to use Docker. Okay.
After that, I have the fourth poll.
Yeah. Oh, okay. This is a trick question. This is a trick question. The question says, I can only work with datasets that fit into a single GPU's memory. True or false? Yeah. So if you have a 16 gigabyte GPU card, can I only work on datasets that are up to 16 gigabytes large? If that were true, how?
100%.
Okay.
All right. Okay, let me just end the poll and share the results.
Very good. Very good. That's right. It's false. You can work with larger than dataset. How? By actually leveraging distributed platforms. So if you are running pandas, like which runs on CPU, if your data structure is larger than your CPU memory, you have to chunk it, you have to partition it. Okay. Same thing with cuDF. Right? When you're working with larger than memory datasets, you will chunk it, you will partition it, and you will sequentially work on that or parallelly work on that. Again, with Apache Spark, of course, we know that's how it works. We integrate with the underlying data structures to make these things scalable, right? As I said, 25% of the world's largest organizations are already on Rapids. Some of the world's largest software platforms like Databricks, Microsoft Azure Analytics, Dataproc from GCP, Snowflake, Cloudera, they all leverage Rapids. Okay? And customers who use that tend to have a significantly better journey. So case in point, we ran a benchmark for a Spark workload, 200 gigabytes, same cluster, so a 16-core CPU cluster versus a 16-core plus 1 GPU cluster. That second cluster had a 5x increase in performance. So it completed the ETL, which was taking 180 minutes. It took 24 minutes. Now, the implication for people who are using elastic computational resources is that you are now taking only 24 minutes worth of infrastructure. So the TCO savings, the cost of ownership, was 78% cheaper. Now, you do this for an organization that has on-prem infrastructure. It's a function of, now that I have this compute, I can do these many ETLs in a day, which is a huge addition, right? The other thing, of course, is backfills. As we spoke about, is very iterative, this process of data science. So when you can do your backfills faster, productionizing data features becomes a less risky offering, because I can just take a couple of seconds and fix it tomorrow, no problem. Compared to, I better not mess this up. It's going to take me 2 days to run the backfill. You see the difference in mindset? So that's why some of the world's largest companies out there are already using Rabbits.
All right. Last poll over there.
Okay. I will sign up for a deep dive workshop via the survey form. Yes, please do. So the thing is, if you sign up, that tells us whether we should run something dedicated and a bit more deep dive for you. If you don't sign up, then what we say is no problem. Then you guys are free to work on your own and learn on your own, and you can come back to us whenever you are available. So if you want to, let us know. And I think the Novorient team, the MPC team, are working very hard. They will try and schedule some of my time to get a session for this group. Okay.
Let me share the results.
Yeah, good. So I think there's a healthy interest from some of you, from most of you. I expect that. So I guess I'll end with a few closing remarks. Right. One of them is that, because I didn't do this when we began, what is it that I actually do for NVIDIA, right? So I'm what we call a technologist. And what that means is I work with developers across ASEAN and ANC. And for us, we quantify organizations as developers, right? So I work with two-person startups to some of the world's largest unicorns in this region. Yeah, you know who they are. And I work with them, I act as their proxy CTO. So I work with them to help them on their AI journey. So I see these workloads. Now, we spoke about how NVIDIA scales. We enable people. Some of the most capable companies out there are finding out that when they start working with NVIDIA, when they start leveraging GPUs, their SaaS offerings become cheaper. Their scalability journey becomes faster, because suddenly as a product, as a billing engagement, you're saying, when you work with us, our specs for your specific requirements are we can complete your ETLs in 30% less time and 80% less cost. Good luck competing with that, right? So that's a journey that ISVs and SaaS platforms see a lot. Students as well. A lot of you, the democratization of AI has been phenomenal. I'm such a big fan. But again, life changes very quickly. I learned Python after my PhD. Okay, I didn't know Python before that. My first job, I learned Python. Okay, so change is the only constant. If you are using MATLAB in your universities today, you may be surprised to find that in industry, very few people use MATLAB. Okay, a few years ago it was R, very good program. Today, very few people use it. Today it's Python. It could be something completely different 5 or 6 years down the line. So keep learning. What you will find out is that the difference between writing code in an academic setting versus a professional setting is as follows. A hobbyist writes code for themselves. A professional writes code for other people, which means you've got to design your code properly. Don't write a class and call it class 1, class _1, class _2. Your colleagues will hate you, okay? So things like that make a difference. When you're writing your code, write it in a way that scales. So if you are interested in learning how enterprises code, how enterprises think at scale, then feel free to fill out the survey form and we'll learn more. Okay, I would also like to thank once again, our partners, NPC, and Novorient for arranging a fantastic session. And thank you, the audience, for a very engaging, attentive presence, for your wonderful, insightful questions, really good ones. And I wish you a good day. Back to you, O'Neill.
Thank you, Dr. Deb, for guiding us through these vast capabilities of Rapid platform, and also sharing with us the applications in this data science, machine learning, and visualizations. And thank you, everyone, audience and Novorient, for joining us today. All right, we can dismiss now. And meanwhile, I would like to invite Dr. Deb to stay on the line while we and Novorient will take a good photo.
O'Neill, I think we remind the audience about the survey form link, which is on the chat box.
Yes, yes. Our participant can fill up the form posted in chat. All right. Okay, let me just turn on Lynn, can you help us to set the spotlight for everyone? Three of us. Is Dr. Edkan on the line?
I don't think so.
He has left.
Yeah.
All right, so three of us. Thank you, Dr. Deb. Really, thank you for your sharing. All right, I'll just take a quick snapshot here. Okay, 1, 2, 3. Okay,
Thank you very much. Thank you so much. Have a good day. Take care. Bye-bye.
okay, bye.
So for all participants who are interested in the deep dive, please use the survey form to indicate your interest with your contact information and business email. And we will discuss with NVIDIA on a suitable date for the deep dive workshop. And it'll be for 2.5 hours. So it's not very long, but you need to have your laptop. And it will be focusing on 2 use cases: financial services and also cybersecurity. So there will be lots to learn, and it will be interesting sessions. So please indicate your interest in the survey form. We look forward to hearing from you soon. Thank you all once again for your interest and participation. See you again. Bye.
Bye, Jacob.